Right, so this is going to be a lecture which is completely hands-on, where I'll be showing you some GPU codes. So the aim is to develop optimized GPU codes. That's the ultimate aim anyways. And then we'll also do some profiling on Jupyter Notebook to show you how you interact with the executables and do some profiling with Python. So the first code we'll work with is a simple matrix multiplication. So I call it case 1, matrix multiplication normal. So that's the code that I had shown you, but I'll show the code to you again. So what we'll do is we'll multiply two matrices M and N to give you the matrix P. M and N both are read from the global memory. So there is no shared memory tiling enabled here. You specify the matrix size, of course. The user should know what the matrix size is, but you also specify the block size in this case. Okay, and this is actually specified as command line argument by the user. There is no need to hard code these things in the program. So when you run the code using ./a.out, you specify the size of the matrix and the size of the block there and then. And in this case, we'll be using 2-dimensional grids and 2-dimensional blocks, because remember we said that grids and blocks can be up to 3 dimensions. So it's always good to ensure that the dimensions of your grids and blocks match with the dimension of the data that you're dealing with. So in this case, we have matrices, so we'll have 2D grids and 2D blocks. So let's have a look at the code. So this is the code, right? So this is simple matrix multiplication. So what you have is you have this kernel called matrix mul kernel, which is to matrix matrix multiplication. You identify the row and column numbers using the block ID and thread ID in both y and x directions. So that again, these codes we have discussed. I'm just quickly browsing through them. I will not discuss these codes in detail again, but feel free to revise them later. So then we say that if row is less than width of the matrix and column is less than width, in this case the matrix is square, so I am not using height and width, I am using width and width. So if rows and columns are less than the width, so basically when you launch threads, you have to make sure you launch only the threads you need. The matrix size could be smaller than the actual size of the threads available. So some threads will not be doing any work because of the reasons we have discussed, that you have warps of threads and you have blocks. So it could happen that you know, they are not exactly matching. So some of the threads which have row greater than the size of the matrix and column number greater than the size of the matrix, they will be sitting idle. So you have to write this if command, and then you simply, for each thread, multiplies a row of m with a column of n. And remember, when it wants an element, it has to access it from the global memory, because that's how it works in this case. And then it iterates over k, which is basically ensuring that it adds an element of a row of m with an element of a column of n. And then once it is done, it's stored in p value, which is a private variable, a local or an automatic variable, which is stored on the registers. And then you simply say p of whatever the element is. Remember, it's flattened matrix. In 2D or 3D, everything is flattened in CUDA C. So you just set p value into that element that you have. So this is the kernel, and this is the main code. So in the main code, you take 2 arguments from the user. There are actually 3 arguments. The first argument automatically becomes the name of the executable you specify, just like we have done in the past in Fortran. And then it just checks if the number of arguments are not equal to 3. It throws an error saying that you have to specify in this format. Then the width of the matrix, basically the size of the matrix, is taken as the first argument from the user. The block size is specified as the second argument from the user. The size of the matrix is width squared times the size of a floating point real number. Then you allocate host memory, allocate device memory, initialize the matrices, copy the data from host to device, very similar to what we have done. Then you decide on the number of blocks and the number of threads. So in this case, you use dim block and dim grid, because you have 2-dimensional blocks here. Block size is the same as what the user specifies, and grid size, the number of blocks per grid, is dependent on the size of the matrix and the block size. You simply do that division, and then ignore these for now. Then you simply launch the kernel using this matrix mul kernel, specify the grid and block, and you pass on the device memory and the width of the matrix. We have these events to ensure that we are able to time accurately the time it takes for the kernel to execute. Okay, this timing is important because I mean, when you time the whole code, it also includes the time for memory copy. So that is what happens if you time this in Python, it times everything. But if you time this using the CUDA event, using a start and a stop, then it allows you to time only the part of the code that was taken to execute the kernel. So that's just for doing some profiling. These codes already have been pushed onto the repository, so feel free to play with them. Again, I don't expect you to be able to write this code from scratch, even I can't write it. So I would typically refer to an old code. So this repository will be available to you during the exam, lab exam or the objective exam. So feel free to have a look at the codes, but you should have understood these codes in the past, what a given line is doing. So if I ask you a question about some code snippet, I give it to you, then you should be able to go through these codes and answer the questions accordingly. Okay. So again, I don't expect you to remember these commands, but if they are available in the repository, you should be able to copy and paste them as needed. Right. So then it prints the time it took for the kernel to execute. Then if there was an error, for example, some of the threads could not launch. Okay, then this error is checked for. I will show you situations where the error will be error message will be printed. Then you have some synchronization, because before you start copying things, although the copying command already synchronizes before that, but this is optional in the sense that all the threads are able to finish first and then you do copying of the data from the device to the host. But again, in this case it is not required as such. And then you have some cleaning up. So let's compile this code. So we need the developer PowerShell. So the code I want to compile is matrix mul cu. So nvcc. The architecture in this case is SM_89. That's the RTX 4050. And then you simply say matrix mul.cu, and the executable name is also the same with an exe. Okay, so it compiles. Let's do an ls. There is a matrix mul.exe which is generated at 11:37 on the 7th of May. Okay, so now next we have to run it. So all we have to do is matrix mul.exe, and then we press enter. Now it says you have to specify the matrix width and block size here as well. So let's do that. I didn't do it, so let's say 1024 and 16 threads per block. So it runs, it says the kernel took 3 milliseconds and the sample output, it just prints a couple of rows. So in our code what we had was we are multiplying two matrices which are both identity matrices. So if you multiply a row with all ones, with a column with all ones, the sum will be just equal to the width of the size of the matrix. So in this case 1024 is what we got. So all the elements are 1024. Okay, so it worked fine. I can play around with this number. So let's call it 2048. It works, and you can do whatever you want with it. Now let me use Jupyter to do some profiling with it. So let's activate the environment that I have created. Conda activate CUDA. So CUDA is being activated, that's my environment name, and then I will say Jupyter notebook. Again, the Jupyter notebook that I will be discussing today has been pushed onto the repository as well. So this launches the Jupyter notebook, and I have this GPU profiling available, so I will just double click it and open it. So in this case we have lots of stuff. First let's clear all the output. So we have case 1, normal matrix multiplication with user defined block size. So what I am doing is I am launching this command from this subprocess.run here, and then I will be timing using this time module in Python, and then I will be printing the output as well from the code. So this is something I have run now. So this uses this executable and sends 1024 and 32. So now we can play with these numbers, and then it shows the output as well. So this with this you can basically play around with. I can actually write a loop for matrix width in these, for block size in this, and I can run it, and for each block size it runs 4 times or 3 times. So now what happens is it starts running it for a matrix of 128 by 128. It runs for 8 blocks, 16 blocks, 32 blocks, and so on, and it keeps doing that for all the cases. In fact, in this case I am plotting things. So this time it runs it, and what it does is it plots for it runs an experiment multiple times. So it prints the execution time for a block size. So block size 16 had 3 runs, block size 32 had 3 runs, and block size 8 had 3 runs, and you can see the spread of the time. So it's not the exact same value. It varies between 90 to 105 milliseconds for each case. Okay. So you can do a couple of things for profiling, because see, you have to decide what the number of blocks has to be. You cannot randomly choose it because you want the code to be optimized. Okay. So that's the first level of optimization. You simply run it for different sizes of the matrix. So this is only for sized 1024, as you can change that here. You can choose a bigger matrix. So basically you play around with this, you basically tune things, try to increase the number of block sizes and see what happens, and so on. The next code we will discuss is with device properties. So let me run it. I will show you the code later. So what this is doing is this code is basically running the same with 4096 size matrix with 32 blocks. It's the same kind of execution, nothing has changed, except that we are also printing the device property. So it's printing what hardware you are using. So it was able to figure out, CUDA was able to figure out what's the compute capability, what's the clock rate, what's the total global memory available. It's a 6 gig card. What's the shared memory per block available, the number of registers per block available, warp size, number of threads allowed per block, number of threads for a given dimension, and so on. So this is a critical number here. The number of threads per block is 1024. So if I set this to 64 and try to run it, then it should give an error. Block size exceeds the number of threads available. So basically you had specified 64 threads per block. So 64 times 64, that exceeded the 1024 sized threads available per block. So this is something that I was able to figure out by printing these device properties. So let me show you the code. This code is called matrix mul dev prop. So here what you do is you simply printing the device properties. So you have this print commands with, you have this prop.name, prop.clock rate, prop.global mem, and so on. So in the presentation I had shown you some of these properties. There are many others available. So it's always good to print all of these first and understand your hardware. But there are situations where you don't know where the code will be running. So for that you want to write a code which is optimized in such a way so that it's able to extract this information and use it. So that's the next thing, which is automatically choose your block size using device properties. So let's look at this code. So this code is called matrix mul dev prop auto. So here what happens is in the main code, this dim block, see, matrix size is you have to decide on the matrix size. Okay, that cannot be chosen optimally, but the number of threads per block can be chosen optimally. So in this case, dim block depends on block dim, and block dim is basically you have something called best block size that we are deciding, and best block size is obtained through this API called CUDA occupancy max potential block size. So what this does is, when you run this API in CUDA, it tries to understand your GPU card. It tries to run some quick things and figure out what is the best block size for this GPU card to maximize occupancy. So that's the level of API. You don't have to go deeper into that. It decides by itself that what is the number of threads per block you should have for the best occupancy of your GPU device. So it does that. It decides on the number of threads which is best block size, but that's a number of threads per block. You want a square block. So you take a square root of that, take the integral part of that, and that gives you the block dim. So let's run this. I will demonstrate that. So it says matrix width is 124. That's what you specified in the code, but this time you did not specify the block size. It chose a block size of 27. So it figured out that 768 threads per block was the optimal number. Through this API for maximizing occupancy, it took a square root of that and chose that 27 threads per block is the best for your case, and it ran it. Okay, so this helps you decide on what's the best block size available. This is when you compiling it, you can use this ptx assembler. So you can simply write minus ptxas-options equal to -v. So that's verbosity. So when you do that during compiling, it tells you that how much of a global memory you are using, how much of registers are spilling, and so on. So this gives you more control of how much of registers you are using per thread. So how much of this local memory or this constant memory you are using. So it gives you lots of information. So it's always good to use these options as well. Okay. Next, let's come to the tiled option, which is matrix mul-tiled. So as we discussed in the class, in this tiling you have these shared memory, MDS and NDS. Actually, let's look at this version. There are two versions. Version 1 is slightly different from what I discussed. Version 2 is what we discussed in the class. So you have these shared memories, and again you may recall that we are using tiling. So we copy a tile of M and a tile of N into the shared memory and then use it as much as possible within a block, because the shared memory is shared within a block. So the tile option is available here. You can run it, and then it shows you, you specify the tile size here yourself, and then it prints the time it took to run, shows the kernel time and so on. Okay. The time it took to run is also includes the time for copying and copying back data from the host to device and device to host, and this is just the kernel time. So this was a very quick journey to seeing how typically you would develop CUDA codes, but this is what I taught you in the class, and you should know all these things if you want to become a good programmer and use CUDA. But what will you actually end up doing is something that's called using this. So you will run this code, and this will use the GPU effectively. So that's using Cupy. Okay. Earlier I showed you in Python you can use something called number.jit. Okay, so CUDA JIT. So that's one way to use CUDA. It was very similar to the way we wrote a CUDA code in C. You had to copy the memory, you had to write a kernel, launch a kernel, you had to copy the memory back to host. Here what you are doing is you are also using CUDA in this in Python code, but all you are using is you are importing import Cupy as CP, and instead of saying a dot of A and B that you would typically say if they were numpy arrays, you say CP dot dot. Okay, and what are A and B? A is a CUDA Py CP dot random dot random. So basically you are creating a random number. So all you have to do is you have to write CP dot something, and that automatically becomes a CUDA Py. It goes to device. So if you have a code which works on CPU in Python, you simply have to start doing CP dot something, and that literally converts this code where you are multiplying A and B using CUDA. So all you do is then you run this code. So you say Python, okay, and this runs. Okay, if you want to check, you can go to your task manager, have a look at the GPU here, and if I run it, you should see some sort of a spike here. You probably see a spike, you saw a small spike here as well, is when it started using the GPU for that short duration. Again, I'm using my GPU card for porting the graphics to the projector, so it's taking a lot of memory from there, but if I was not using the projector, I could simply see a spike. So these spikes are basically where you are running the GPU codes. Increase the size, you see a better spike. So the idea is that it's as simple as, so first run, I mean of course you don't have a lot of control here, you are not specifying the number of blocks and so on, it optimizes everything for you, and that's the best thing to do at prototyping stage. But once you start going deeper and deeper into writing optimized programs, you may have to go to CUDA C, but always start with Cupy, that's the easiest thing to do. Then what I would do is I'll try with Cupy, then I'll go to Numba. I'll write the same program with copying kernel, copying back to the host in a Python environment, because again it's much easier to do prototyping there, and then I'll go to CUDA C. So I leave it to you to go back home and try to run all these on Param Himalaya, and also try an if-else branching. I didn't show that to you, but remember we discussed that if you do an if-else branching which results in controlled divergence, it will drop the performance. So you have to be careful with having too many if and else statements, because that creates divergence in the control sequence. So that's sort of the end of CUDA, and we still have to discuss about OpenACC, but that will be a very brief discussion, because OpenACC is very much like OpenMP, and given that now we understand the architecture, both compute architecture and memory architecture in the GPUs, we don't have to discuss too much in terms of OpenACC. I'll just show you a code. I'll run it on Param Himalaya because hopefully we'll get some resource there, because I didn't install OpenACC compilers on my local machine. They're available on Param Himalaya, so I'll try to run them there and demonstrate the speed up we get by simply having a CPU based code, and like OpenMP we just put in some pragmas or directives before the for loops to do some quick parallelization of loops in the code. I'll show you both I think I have a Fortran as well as a C version, so I'll try to show you both if possible. Okay, so that's stop the recording here.